So this is problem number 1 on the review sheet. It says the figure below shows a potential energy diagram of the total energy line of a 2.5 kilogram mass oscillating on a spring. What is a spring's equilibrium length? Well, if I take a look, equilibrium happens where you have no potential energy. So if I just go down right here, it looks like the equilibrium length is 20 centimeters. So that's just the length of the spring, 20 centimeters. So when it's relaxed, it's just 20 centimeters long. Where are the turning points of the motion? They're right there and right there. So if I go down there and there, looks like it's halfway between 12 and 16-ish. So if we, that's about half, I guess. So we'll call it 14. So 14 would be one and 26 would be the other. So 14 centimeters would be one turning point, and then we said 26 is the other one. What is the amplitude of motion? Well, if the equilibrium is at 20 and it goes all the way to 26, so it starts at 20 and goes all the way to 26 and goes back 20 and goes all the way back to 14, then we're looking at about 6 centimeters would be my amplitude. What is a particle's maximum kinetic energy? Well, my maximum kinetic energy is going to happen here, so this is the total energy up to that spot. That looks like about 7 joules by looking at it, so I'm just going to say 7 joules. All right, so remember, these are energy functions. That's just 7 joules to go there. My maximum potential energy would be 7 joules there. So maximum potential energy is always from there to there, and then the total energy line to where the potential energy is the lowest is my maximum kinetic energy. Determine the maximum speed. Well, if we know that kinetic energy is 7 joules, kinetic energy is equal to 1/2 mv squared. So V is equal to 2 times the kinetic energy all over the mass, square rooted. The kinetic energy is 7 joules. The mass is 2.5 kilograms. I then square root that. So I get 14 divided by 2.5 and then square root that. My maximum speed is 2.37. So 2.37 meters per second. And remember, that's happening at equilibrium. So go ahead and write that there. 2.37 meters per second. Determine the spring constant. All right, well, here's the thing. We know it's a mass spring system, and so when we get here, at this spot here, let me go up a little bit more. When we get to this spot here, we have no kinetic energy. The total energy exactly equals the potential energy. We know potential energy for a mass spring system when there's no kinetic is 1/2 K A squared. Okay, so I know that the potential energy is 7 joules. I'm looking for K, so K would equal 2 times the potential energy at maximum at amplitude, or in this case I'll say 2 times the total energy, doesn't really matter, all over A squared. So that's 2 times 7 joules. The amplitude we already said is 6 centimeters, so that is 0.06 meters that is squared. And so 2 times 7 divided by 0.06 squared, I get about 30, I'll say 3,900 newtons per meter. So this is a pretty stiff spring. I got 3,888 and then 8 repeats, 0.88888. So I just rounded it up to 3,900 right there for the determine the spring constant. So 3,900 newtons per meter. Determine the frequency of oscillations. We know that the period is equal to 2 pi the square root of m over k. If we invert that whole thing, we actually get 1 over 2 pi times k over m square rooted. So if I plug in that in, I get 1 over 2 pi. The k, we'll just say 3,900 newtons per meter, all over my mass of 2.5 kilograms. I square root that. 1 divided by 2 pi. Okay, and then times the square root of 3,900 divided by 2.5. I'm getting an answer of 6.29 hertz. So 6.29 hertz is my frequency. So I'll go ahead and say that over here, 6.29 hertz. It says write an equation of the motion if the object started at t equals 0 seconds at amplitude. I don't know the reason for that, but So what we're going to do is we're going to start at amplitude at t equals 0. So we want the cosine function. So as basically x as a function of time is equal to a cosine omega t. We don't have to worry about phase because we're starting at amplitude at t equals 0 seconds. Okay? And so what I'm going to do is we know that omega is equal to 2 pi f. So that's 2 pi times the frequency, which we got to be 6.29 hertz. And so 6.29 times 2 times pi, we get 39.5. So 39.5 radians per second. And so if I write a function x as a function of time, we know the amplitude is 0.06 meters. We got that from the graph. You can say 6 centimeters is fine. Cosine of 39.5 t. Okay, and remember, if we don't put a unit, we can assume it's radians per second. So that would be my expression. And then, so what will be the turning points if the particle's total energy is doubled? So if I go from 7 to 14, what I'll just need to do is the total energy is doubled. So now I go to 14 joules of energy. So my turning point would be there and there. Looks like, I mean, if I drew this a little better, looks like it's going to be over 28, so it could be 29-ish, and then this looks like it's going to be a little less than 12, so those would be my turning points.